Okay, so hopefully things are properly getting recorded. Okay, so we continue in class 16 with calculation of average kinetic energy of a particular particle of an ideal gas. So the average kinetic energy of a particular particle in an ideal gas is also the average energy of the system, because in ideal gas there is no potential energy. As a consequence, as a consequence, so this actually is the expression, the correct calculation of the equipartition theorem, because in the previous calculation in the previous week we had shown that the average energy of the system, uh, n particle system, is 3 by 2 nkt for 3D, using the calculated in the canonical ensemble, where a system of n particles in volume V uh, at temperature T uh, could take energy from the reservoir, and the corresponding set of microstates correspond to the canonical ensemble, because energy can fluctuate and as different from the microcanonical system. I mean, I think I've repeated this so many times, I'll just stop repeating in the future. But we had shown that the average energy for n particles in 3D is 3 by 2 kBT into n. But here what we're going to do is show or let you calculate the average kinetic energy for one of the particles, suppose for even 1 degree of freedom. So the way to go about calculating it, so this is, in that sense, is the actual calculation of the equipartition theorem, because for each degree of freedom which are quadratic in the Hamiltonian, the kinetic energy, I mean, the kinetic energy is quadratic in the Hamiltonian, and hence it will be shown that for each degree of freedom, the energy, the mean energy will be half kBT. So here what we are calculating is for, suppose, the ith particle, any ith particle, the x component of the momentum. So this is the energy pix whole square by 2m, is the energy corresponding to the x component of the momentum. The x component of the momentum can take any values from minus infinity to plus infinity, and corresponding to that degree of freedom, the momentum, uh, right, for the ith particle, the x component of the momentum for the ith particle, where the x momentum can take minus infinity to plus infinity values, what is the mean energy correspond to that? And the way to calculate it is basically take take the value of the variable, in which this case is px square by 2m. So the value of the variable xi uh, into probability of that particular microstate, right? So the probability of that microstate can be written as e to the power minus beta 2m pix square plus uh, all possible other degrees of freedom. So that is written from minus infinity to plus infinity. So this is dpix into all other degrees of freedom, x, y, z, 2m, kbt, dpx1, y, z, for all particles, and so on and so forth. But we are interested only in this, the average value of this, right? And as long as we fix this, so this will essentially, we are writing down the energy of that entire microstate here, but what we see is the other degrees of freedom. So j equal to 1 to n, or if you like 1 to 3n, if you have x, y, and z coordinates, except I, So these degrees of freedom are decoupled from this. So that's why I have written this separately and all other degrees of freedom separately. And this is j equal to 1 to 3n. There should be 3n except I, right? And the numerator, So what are you doing? We are doing is figuring out each microstate and the probability. So the probability of accessing different microstates is minus beta by 2m, this expression, and we are summing over all. We are doing an ensemble average, so we are allowing all momenta to vary from minus infinity to plus infinity. We are doing an ensemble average, sum over all microstates, probability of that microstate, and the value of a particular variable in that microstate. So this is xi, this is this, and this without the integral sign is the pi, and for the pi you also need z, right? Pi is e to the power minus beta e, so these are e over z, but then we have to sum over all microstates and all values of the variable. So this sum is represented by this integral minus infinity to plus infinity. This sum over all microstates where this variable can vary and this variable can vary, and the probability when the different microstates are accessed are given by this, by z, right? And by this integral we are doing an ensemble average. And of course we also had to do a real space average, but those are decoupled to p square. Hence you get p to the power n, right? N factorial 1 by h cube. Well, you will actually have 1 by h to the power 3n, or rather 1 by h cube for this, and again for each degree of freedom x and dpx, you will get h, right? So if you have n particles, you will have h3n. But so will there be in the partition function. In the partition function also, you will have e to the power n factorial 1 to the power h to the power 3n. Here also you will have 1 upon h to the power 3n. The only and you will also be integrating over all the variables. The only thing that you don't have is this term. Pix square is what you don't have, because in general partition function is e to the power minus beta h, where each of the variables can take all the possible values allowed, right? So px goes from minus infinity to plus infinity, and x goes from 0 to lx, y goes from 0 to ly, z goes from 0 to lz, where lx, ly, lz are the dimensions of the box, the boundary condition. So when you integrate the position of each particle over the entire volume accessible, you get v to the power n, right? So the terms in the numerator and terms in the partition function are nearly identical, except for the ith variable, right? So pix whole square. So if you had, so this is the variable, this was the e to the power minus beta ei term, and we are integrating over all microstates, right? All the values of the variables at the microstates. Note that there is no time here. Only the variable px is changing, the variable x is changing, which is giving v to the power n. And if you calculate these terms, j equal to I to the power 3n actually, if you are doing it in 3D. However, if you are doing it in 1D, then it would be n. So it really depends. So except I, So this and this would be identical. The only thing which will be different, which you will calculate differently, is this term, and this will get so sorry, this again will be dpx, right? It won't be x but dpx. This will give 2 pi m kbt to the power half. You know that. However, this will give you a different value. As a consequence, what you will get from this, if you carry out that integral, is half kbt. So for each degree of freedom, the kinetic energy, the mean kinetic energy for each degree of freedom individually will also be half kbt. Not only that, it's an average over n. For each degree also you will get half kbt. So that's the actual proof of the equipartition theorem. You just calculate it from your partition function, and all that matters is doing these integrals, where many of the integrals will cancel. The only integral that you have to do is this versus divided by this. These terms like this will cancel, right? So that's the message. So the next thing that we're going to do is taken from Rife section 7.9, 7.10. By the way, these things are there in multiple books, including Rife. So you can just look up Rife, Patria, Kardar, Huang, whichever. Equipartition theorem is there in every book. I think this is from Rife or Huang, but I'm not sure. Okay, this is standard equipartition theorem. This part is definitely taken from Maxwell Boltzmann from section 7.9 and 7.10 of Rife. So just to start off, what do we plan to do? So we plan to, so all that I've written down is the probability of a certain microstate, right? For a canonical ensemble, that is a system with volume V, energy, number of particles N, and energy EI. So here you have I, so here it should be I of a particular microstate I. Now this is a microstate of a system in contact with a reservoir at temperature T, right? So the energy can fluctuate. EI is not fixed. Different microstates can have different energy. What is specified is beta, the value of temperature. Beta is 1 by kBT. And the question that we are asking, so we're going to derive this from the canonical distribution. But at the moment, the question we are asking is how many particles, dn, how many particles have velocity between v vector and v plus dv vector, and also are located in position r, are located between r and r plus dr. So what does this mean? So you are looking at a particular system. Now the system is in contact with a reservoir, which I have not shown. So suppose the system is the room in contact with the city of Pune. The city of Pune is not shown, and what we are interested in is dn, the number of particles contained in a small volume element located at R. The volume element is spreads from x and x plus dx, y and y plus dy, z and z plus dz. So it can be also written as d3r. So the volume element is d3r at a position r. So it is, so the number of molecules located between r vector and r plus dr vector. So where dr vector, so x varies from x to x plus dx, y varies from y to y plus dy, z varies from z to dz. So thereby you get a cube. And moreover, so here there can be many particles, but we are interested in only those particles, or in the number of particles whose velocity lie between v vector and v plus dv vector, which means their velocities the magnitude of the velocities are between a particular Vx. I'm not talking about the magnitude, x component, it has to be plus or minus, whatever. Vx and Vx plus dVx, Vy and Vy plus dVy, Vz and Vz plus dVz. So there's a certain, it's a velocity is also a vector. The velocity is between V vector and V plus dV vector. So there might be, here there could be particles which are moving in the negative direction, in the positive direction, positive z direction, positive x direction, positive y direction. But we are really interested in a subset of particles, and we want to estimate, or we want to have an idea about the number of particles within such coordinate system, right? And of course, if we divided by the total number of particles in this box, we would get essentially the fraction of particles which are moving, which are located here and moving with a certain velocity vector within this certain range. And that would also give an indication of the probability that we want to find gas particles in this vector volume, right? And let's write that. So this dn by n, the total number of particles moving with this constraint, divided by n. So this quantity dn can be written as FVR, some function which we shall realize it to be the distribution function, into d3r into d3v. So here there should be a 3 here. I mean, we are talking about a vector. I mean, so it's something like this. This should be a d3v if you like. Right. So basically, this quantity FVR is the number of particles moving with velocity v. When we mention velocity v, it means between velocity v and v plus dv, and in position r, which means r and r plus dr. So this quantity is the number of particles per unit volume of phase space, right? So this quantity is the number of particles per unit volume of phase space. So that's what that is the meaning of FVR, right? And dn by n would be the probability or the fraction of particles which are moving in that. So with that meaning, so if we integrated FVR over all volume in V, this real space, and all allowed velocities, we would be getting n, right? So FVR by n is, if you like, the probability density. But let's discuss this point a bit later, right? Why is this coming here, not disappearing? I don't know. This should not appear, but never mind. So now if we look at the number of molecules in D3R, right? If we look at the number of molecules within a small volume element, real space volume element, and that is in contact with all the other molecules within that element. So with respect to that particular molecule, the probability that it will have a certain velocity v or speed v, if you like, so that will depend upon the energy of the molecule, because the more energy it absorbs, so it's basically like a small system in contact with the reservoir within the volume D3R, right? I don't know why this is. No. Okay, that's better, I hope. So what I'm saying is, so suppose look at a particular molecule within the room, within that small volume element D3R. So it is surrounded, of course, by that entire system as well as the molecules in the D3R bit in D3R, and the probability that that molecule is going to have higher and higher energy is e to the power minus beta EI, where I is the energy of that particle. Right? That even that the velocity that it will have a particular velocity VI vector will be proportional to e to the power minus beta, and corresponding to that particular velocity vector VI vector, there will be a certain value of the kinetic energy. So VI, so here this VI means Vx square plus Vy square plus Vz square, because we are talking about a particular velocity vector, and the probability that the system, that a particular gas molecule in D3R will have a particular velocity vector Vi will be proportional to, because it is taking energy from a reservoir. If you can think of it, that it's taking energy from a reservoir as e to the proportional to. So I have written it equal to C dash, right? Dash e to the minus beta m kinetic energy of that molecule. We are talking of ideal gas. So at the moment we are not worried about the potential energy, but you would see that even if you had potential energy, since the momentum degrees and the positional degrees are not coupled, it would not matter. So basically, terms, if you had extra terms in the partition function, they would simply cancel out. You would see that. I mean, we can see that later. Right. So in that case, since each individual molecule is independent of the other, so then FVRD3RD3V, which is the number of molecules at position R moving with velocity vector V, yeah, so would be, so since each molecule is uncoupled with each other, they're separate from each other, is proportional to some other constant C, e to the power minus beta p square by 2m, the velocity of each of these, the momentum, so this is essentially p square by, this is the same as half mv square, the momentum of each of these molecules, and they are independent of each other. So this will be some other proportionality constant C, and it will, of course, the number will of course depend upon the size of D3R. If the D3R has a larger volume, there will be larger number of molecules moving. There will be the value of dn here would be more, and so this is per unit volume of phase space. So if d3r is more or d3v is more, the number of particles moving at r and r plus dr and v plus dv will be more. So this is per unit volume, and this is multiplied by the volume that we are considering, right? So because if you have more particles, there will be more there will be more this proportionality constant will be higher, right? So yeah, so load, and so within each, the thing to remember that in each volume element of phase space, d3r and d3p, there will be a large number of molecules which can have the velocity v, right? And this quantity is giving a count of all the molecules which have a particular velocity v vector, right? Of course, now if you integrate, so this is like dn, right? So this is like, this quantity is like dn. Now if you integrate over all the momenta and all the velocities and all the accessible position, so dn, so basically dn means you can count in within a certain volume with a certain value of velocity vector v, there is a certain dn v moving. But within the same volume element, there would be a separate number moving with velocity v2, a separate number moving with velocity v3, a separate number moving with velocity v4. So within d3r, if you integrate over all the allowed values of velocity, then you would get the total number of particles within d3r moving with any velocity, right? And now if you integrate over the entire volume, all the different values of d3r that is possible, then you will get the total number of particles, right? The integral was here over d3v. All that I have done is converted this d3v to d3p, because you know the expression of the integral, and while converting v to p, I had to divide by m cube. That's all that I have done, right? So what is the aim? We are doing this integral because we don't know what is this normalization constant. We know that each particle at a certain volume, what this is the probability, it will be c dash, and then we multiply by d3r and d3v, this will be a certain c, right? This was the velocity of an individual particle. Here we are calculating the number of particles uh, with velocity v and vector r in d3r and d3v, right? So I've mentioned it's also located at r, and our aim is to calculate this normalization constant. Now the calculation of this normalization constant is actually, if you realize, pretty easy. Note, the other thing to note is, while calculating the partition function, we are integrating individually over all the degrees of freedom. Here we are not doing that. Here we are starting from a different premise. We are saying how many particles are moving at r with velocity v and v plus dvr. So this already is a statistically large quantity, right? So this is already a statistical quantity, the density, so the number of particles per unit volume, right? So when we integrate, we are just integrating over all the possible values of v which are allowed. For each different increment in velocity v, there are large number of particles which are possible, right? So each velocity for a particular velocity vector can be occupied by a large number of particles. A smaller fraction will be at a particular position r. So here the integral is not over all 3n degrees of freedom. The integral is over just one variable px, py, pz, which can take any value, and you are asking how many particles are between any particular momentum and momentum plus dv. And similarly about positions, because you are saying at a particular position in space, how many particles are there, right? So here the integral is not over 3n. That is the thing to emphasize. And then this is just a Gaussian integral. It's a Gaussian integral c into, you can calculate this, and this is 2m kbt, 2 pi m kbt to the power 3 by 2, because there are 3 degrees of freedom, x, y, and z. And if you had 2, you would not have 3, but you would just have 2. And this gives again v, because we are integrating over all the volume and asking, okay, at each volume element, how much particles are there. So we're just integrating over the volume element. This is the thing to note and how different it is. Let me not repeat this same thing over and over again. So you get v here, this n cube is intact. This integral gives 2 pi m kbt to the power 3 by 2 into n. Therefore, c you get immediately as n by v m cube 2 pi m kbt to the power 3 by 2, which can be written as there's an m here and m to the power 3 by 2 here in m cube. So the m comes here, m by 2 pi kbt to the power 3 by 2, right? So now we have an expression, an explicit expression of FVR. So this quantity is the number of gas molecules moving with velocity v at position r, and that is equal to n. This is the number density. Remember, n by v is the number density. M by 2 pi kbt to the power 3 by 2 mv square. We are asking how many molecules at velocity v, mv square by 2. I think this should be beta. Yeah, so I've confused p square by 2m. So here it should be beta m half mv square. This m should be missing. There should be a beta here. And just multiplying d3r and d3p. If this is more, the number of particles moving will be more. This is the density of particles, right? So we have an estimate of the number of gas molecules moving between d3r and d3p, and it's of course depends upon the density of gas molecules. Think about this, right? And if we are calculating dn by n, then we are calculating, this is the fraction of gas molecules which are at position r moving with velocity v vector. R vector, v vector, where it is implied the velocity is between v and v plus dv. The position is between r vector and r plus dr vector. Right. So I'm just repeating this. So this was the number of gas molecules. Okay. So now we are asking a different question. Now suppose we are not interested in v vector, but just the speed. So as long as the speed was within a certain range between v naught, we are interested in the absolute value, and v plus dv, right? So all of these are scalar quantities. We are not interested in v vector, but how many particles have a velocity within a thin spherical shell? The shell is of width dv, and you really don't care about the direction as long as its speed vx squared plus vy squared plus vz squared is within a certain range. We want to calculate all those particles. Then what we do is we do a vector integral. We don't care about which vx, vy. It's not a vector. We are interested in the scalar. So what we do is, so we can still ask whether we want the number of particles within d3r or over any volume. So if we want over any volume, then we also integrate over all r space, and moreover we integrate over 4 pi v squared dv. This is basically converting dvx, dvy, dvz from a Cartesian integral to a spherical polar coordinates integral, right? So this is the shell. This is that 4 pi r squared dr type of shell, right? So we are doing that, and we have to integrate for all particular directions because we don't particularly care about any direction. So we have integrated over theta and phi here, and that's how we get this 4 pi, right? So what we get here in turn is dnv, right? So total number of particles moving between v and v plus dv in the entire box, because we have integrated over d3r. We don't care about any particular whether the particles are located at r vector or not. Over all space we have integrated d3r. Moreover, we have integrated over all directions in velocity. So d and v, this is a scalar v, and in volume, sorry, I think this is meant to be a volume v. Yeah. So we have integrated over d3r to get this v e to the power minus mv square by 2m n by v, as we had got previously. Right, the expression for FVR. This was the prefactor, m by 2 pi kbt to the power 3 by 2, 4 pi v square into dv. Right, if dv is more, the number of particles is more. Right, and dn by n is then 4 pi v square, 4 pi v square, m by 2 pi kbt to the power 3 by 2, e to the power minus mv square by, so this should be beta, there should be a beta here, I don't know why I have written 2m here. So this should be beta mv square by 2, or mv square by 2 kbt. I'm sorry for this mistake, and dv. Now this essentially is the probability density. So this quantity was the probability, I mean fraction of particles if you like, which would be proportional to the probability. On the other hand, so this is the probability of finding so many particles between velocity v and v plus dv, right? On the other hand, this quantity is the probability density, probability per dv. On the other hand, if you multiply by dv, you get the fraction of particles or the probability. And this quantity is the probability density. That is the distribution function. That is what we call as the Maxwell Boltzmann distribution function. You might have come across it in the past from the kinetic theory, but this we got essentially as a consequence that each microstate or higher energy microstates or higher energy particles even access higher energies with the probability e to the power minus beta ei. It came from the canonical distribution, right? How the energy of particles in a system which is exchanging energy with its reservoir, what is the energy of the particles there? So that's where we derived it from, right? And the distribution function or the probability density is 4 pi v square m by 2. So m by 2 pi kbt to the power 3 by 2 mv e to the power beta mv square by 2, or mv square by 2 kbt. So this is wrong, of course. Right? And how does it look? So if we call this the probability density or the distribution function for the particular temperature T1, then I would ask you to note that you have a v square into e to the power minus mv square. So if the x-axis is a function of v, then p of v is v square, which is a sharply increasing function, right? And into an exponential function, which is a sharply decreasing function. As a consequence, this has a fixed peak. And moreover, you have to note that this function, this distribution function, is not symmetric, right? So if you plot it, you can do a curve, you can do a graphical plot analysis, see that it rises sharply here, but falls more gradually here, right? If you calculated PV dV, so that would be a small rectangle like this, that would give you the probability to find a particle between V and V plus dV. So this is probability density, right? Probability by dV. Probability would be obtained by multiplying this quantity, the distribution function, by dV. And if you integrated over PV dV integral over all values of the velocity, you will get equal to 1. Now, if you plotted the same quantity at a higher temperature, then of course the system can access higher energies. So the system will have higher kinetic energies. Hence, the peak will shift. The peak of the distribution will shift from this point to the point where it has, suppose, the high, and so it's not the V max, but the point where this curve has the velocity at which this PV has the maximum. Let's call that V max. Now, at a higher temperature, if T2 is greater than T1, it is going to shift to higher temperatures. Right? So this entire distribution. Moreover, the highest kinetic energies, so we are talking about velocities, the highest velocities that it can access, because it is at a higher temperature, it can take more energy from the system. Thereby, it will be also more spread out. But remember, the area under the curve, PV dV, has to be equal to 1. Right? So here you see that this is sharply peaked here, there is a higher peak, but it falls more rapidly. Here the peak is lower, but it is more spread out. But PV dV integral over the entire range of the speed will be equal to 1, and it is a consequence, the shape of the curve is a consequence of a product of v square minus into e to the minus mv square by 2m kbt. Again, I don't know why I keep on writing m here. I'm extremely sorry for this. Right, but you get the idea. And this is called the speed distribution, because we are not looking at a particular velocity vector. So we are really interested in the number of particles, or the distribution of probability density of particles between v and v plus dv. And this is the Maxwell Boltzmann speed distribution. Right? And just to emphasize again, PV dV is the probability, right? Not PV. PV is the probability density. And this will come useful in your computational physics course as well, if you remember it. And if you don't, well, you'll have to realize it. The last point in this discussion is the distribution of a component of the velocity. So that was speed. Now we are discussing velocity distribution, or more accurately, distribution of a component of the velocity. And that will be, so we start again from here, the number of particles at position r with velocity v. So in d3r and dv, right? And that, as you know, is m by 2 pi kbt to the power 3 by 2. Number density, e to the power m beta by 2. Thankfully, here everything correctly, no m here. Dx square plus vy square plus vz square, d3r and dvx dvy dvz. Now we are interested in the number of particles between vx and vx plus dvx, particular component, right? So what we're going to do is let all other components, y and z, take all other possibilities. So we do an ensemble average over vy and vz. But we calculate the number of particles which remain between Vx and V plus dVx. So the number of particles between Vx and Vx plus dVx in volume d3r is when we integrate for all possible values. Let the y and z components take any value that they want. We suitably weigh it. The weighing factor is here, right? Vy square, Vz square. But we are not allowing Vx to vary freely. We want the number of particles for a particular values of Vx, right? So we are integrating over Vy square and Vz square, but not over Vx square. Hence, we are integrating over dvy and dvz. So if we integrate that, we will get n into m by 2 kbt to the power half, right? Because those integrals are going to give suitable factors, and hence from 3 by 2 this will become half. This n will remain intact. E to the minus v m vx square by 2 kbt dvx to d3r. Now, if you want to do it, put it over entire volume, or I mean the distribution function is essentially this quantity. Whether you do it per unit volume or whatever, the probability density or the distribution function is this quantity. Note here the x-axis is not speed, but Vx, x component, a particular component of the velocity. And in this case, you have minus mvx square by 2 kbt. So this is a Gaussian. It's not Vx into this. This is mvx square by 2 kbt, and this is a Gaussian, and this is to be distinguished between the speed distribution function, where because we had integrated over all directions, we had got a 4 pi v square. So this function runs from 0 to infinity. This was a non-symmetric function, v square into e to the power minus mv square by kbt, whereas this runs from minus infinity to plus infinity. It's a Gaussian function. The distribution function is this quantity for a particular velocity of component, for a particular component and velocity of velocity. So I'm going to leave it at this. You work it out, the steps, but I'm focused on the physical meaning. We shall continue from next class.